Imagine a moment when everything you thought you knew about the universe is turned completely upside down. The James Webb Space Telescope, humanity's most powerful and cutting-edge scientific tool, has just made a discovery so shocking that it's rewriting the very rules of cosmic understanding. 7 massive galaxies, defying every expectation, have emerged a mere millions of years after the Big Bang. How did they form so quickly? What mysteries do they hold within them? This groundbreaking revelation challenges the very core of how we believe galaxies, stars, and the universe itself came into being. It's a discovery that forces us to reconsider everything we thought we understood about the cosmos. In this video, we'll take you on a thrilling journey back to the dawn of the universe, where the answers to our deepest questions lie waiting in the farthest reaches of space, places we never imagined we would reach. Part 1. The astonishing discovery: 7 colossal galaxies prepare to have your understanding of the universe completely turned on its head. The James Webb Space Telescope, with its unparalleled sensitivity and cosmic reach, has uncovered 7 massive galaxies that existed only a mere 550 to 750 million years after the Big Bang. These galaxies are far from the small, simple systems that scientists expected from such an early era. Instead, they are colossal, complex, and over 60 times larger than theoretical models predicted for galaxies that emerged so early in the universe's history. This discovery has shaken the very foundations of our understanding of galaxy formation. To truly grasp the significance of this, let's step back for a moment. The Big Bang, which marked the beginning of our universe, occurred approximately 13.8 billion years ago. Just hundreds of millions of years later, the universe was a chaotic expanse of particles and energy, only beginning to settle into the basic building blocks of stars and galaxies. Scientists had long believed that the first galaxies to emerge would be modest in size, composed of young, bright, and blue stars, hot stars that burn quickly and die young. However, what Webb has shown us is something entirely different. The galaxies observed aren't dominated by young, blue stars at all. Instead, they are teeming with ancient red stars, the signature of maturity. These red stars are cooler and older than their blue counterparts, suggesting that these galaxies must have started forming stars almost immediately after the Big Bang, far earlier than we thought possible. This revelation presents an enormous puzzle. How did these galaxies grow so rapidly? Traditional models of galaxy formation tell us that galaxies require billions of years to grow, accumulating gas and dust over time to form stars, expand, and mature. Yet these galaxies, some of the largest and most developed ever observed, achieved this in a fraction of that time, suggesting that we are missing something fundamental in our understanding of cosmic evolution. Even more astonishing is the sheer scale of these galaxies. They are not just larger than expected, they rival and even surpass the size of our very own Milky Way galaxy. To encounter such enormous, mature galaxies so soon after the Big Bang is like finding a massive, fully grown tree in the midst of a field of saplings. So, how did these galaxies become so massive and complex in such a short amount of time? One possibility that has scientists excited is the idea that these galaxies aren't isolated. Instead, they might be part of something much larger, a protocluster. Protoclusters are the precursors to galaxy clusters, vast networks of galaxies bound together by gravity. These structures form some of the largest, and most intricate features in the universe. Within these dense cosmic environments, galaxies can interact, merge, and trigger bursts of star formation, accelerating their growth at a much faster rate than they would on their own. It's like discovering that these galaxies were born in cosmic nurseries, environments rich with the necessary conditions for rapid formation and evolution. But this hypothesis only deepens the mystery. If these galaxies are part of such protoclusters, how did these clusters form so soon after the Big Bang? The formation of protoclusters would require a significant concentration of dark matter, that mysterious, invisible substance that makes up roughly 27% of the universe. Dark matter generates the gravitational forces necessary to draw in gas and dust, allowing galaxies to grow. This would suggest that dark matter played an even more essential role in the early universe than we previously realized. Could dark matter have helped create the conditions for rapid galaxy formation in a way we didn't anticipate? Perhaps we are missing some crucial piece of the puzzle, a hidden force or unknown mechanism that allowed these galaxies to form at an incredibly fast pace. This discovery isn't just rewriting the history of galaxy formation, it's pushing us to rethink everything we thought we knew about the cosmos. Part 2, Time and Distance, a journey to the early universe. The James Webb Space Telescope has given us the most breathtaking glimpse of the distant past, capturing light that has traveled for a staggering 13.5 billion years to reach us. The galaxies Webb has observed existed when the universe was only 6% of its current age, just 750 million years after the Big Bang. This isn't just about looking far away, it's about peering into a time when the universe was still in its infancy, a place where stars and galaxies were just beginning to form. Thanks to Webb's unrivaled sensitivity and ability to observe in the infrared spectrum, we're able to peer deeper into space than ever before. Unlike visible light, which fades as it travels across vast distances, infrared light can penetrate through the vast voids of space, carrying with it a record of events that took place billions of years ago. Webb's infrared capabilities allow us to see further back in time than was ever possible before, providing us with a powerful tool to understand the universe's beginnings. What makes this journey back in time even more fascinating is the phenomenon known as redshift. As the universe expands, the light emitted by distant galaxies stretches, shifting toward the red end of the spectrum. Imagine hearing the sound of a siren from a passing ambulance. The pitch lowers as the vehicle moves away. In the same way, light from ancient galaxies stretches as it travels through space, its wavelength growing longer as it shifts into the infrared range. Redshift acts like a cosmic fingerprint, telling us not only how far away these galaxies are but also how long ago they existed. For the galaxies Webb observed, their extreme redshift tells us that their light began its journey when the universe was still chaotic, filled with gas, dark matter, and nascent stars. The universe hadn't yet formed the elements we take for granted today, such as carbon and oxygen. The light Webb has captured is like a time capsule, offering us glimpses of the first tentative steps of a universe that was still learning how to build itself. Part 3, Challenging the role of supermassive black holes. For decades, scientists have believed that supermassive black holes are crucial to the formation of large galaxies. These cosmic giants, millions or even billions of times the mass of our Sun, anchor galaxies, influencing their structure and growth. Through a process known as feedback, supermassive black holes regulate the pace of star formation by expelling or heating gas. However, the discovery of these 7 massive galaxies challenges this long-standing belief. The galaxies Webb observed, despite their vast size and mature stars, show no clear evidence of central supermassive black holes. These galaxies seem to have formed and grown without the typical feedback mechanisms that black holes provide. If these galaxies grew to such enormous sizes without black holes playing their usual role, how did they manage to develop so quickly and efficiently? One potential explanation could lie in the existence of supermassive stars, stars that are much larger than anything we see today, formed under the extreme conditions of the early universe. These supermassive stars could have catalyzed rapid star formation within galaxies, driving their growth without the need for black holes. If this theory holds true, it would fundamentally alter our understanding of how galaxies form. Perhaps the early universe didn't rely on black holes for structure and growth, and instead, other mechanisms, like supermassive stars, took their place. Part 4, Challenging the dark matter theory. For many years, dark matter has been the cornerstone of our understanding of cosmic evolution. This invisible substance makes up roughly 27% of the universe, and it is believed to create the gravitational forces needed for gas and dust to coalesce into galaxies. However, the discovery of these massive galaxies early in the universe's history challenges this theory. The galaxies observed by Webb are simply too large and mature for their age, contradicting the current understanding of dark matter's role in galaxy formation. If these galaxies could grow so massive and complex in such a short period of time, perhaps dark matter doesn't operate the way we thought, or maybe we're missing an essential part of the story. Could there be other forces at work that are still hidden from our view? The answers to these questions could completely transform our understanding of the universe's evolution. As the James Webb Space Telescope continues its mission, the discoveries we're making challenge us to rethink our place in the universe, and the very forces that shape it. Each new discovery takes us one step closer to answering the most profound question of all: where did we come from?